Thank you. Good afternoon, everyone. My name is Philip Law. I'm with Facca, which is a company based in Ruscombe, Ontario, which is near the Windsor-Detroit border. Dura Concrete Canada is a company owned by Facca. It's a joint venture with Dura Malaysia. And I want to thank all my other authors, co-authors, Dr. Mel Tedros from eConstruct, Greg Lucille from North Carolina State University, Adam Sevenker from eConstruct, and then my boss, Don Gadonio. For health reasons, he couldn't be here today. So anyway, let's start with this project that we did in Ontario. So just to give you a brief background, and then design, fabrication, and testing. That will be the outline. This project was part of the main project, which is sponsored by PCI. It's a study on the implementation of UHPC structural elements for bridges and buildings. And PI is eConstruct USA. So those are all the contributors to this project. eConstruct, WJE, all the Ohio State University, Nebraska, and then North Carolina. And then there are 6 participating precast company, 5 in the U.S., and then Facca, obviously from Canada, and then the other 2 companies that deal with the formwork. All right? So why do we use UHPC? This is just a comparison of the environmental impact numbers. Like when we compare precast box beam, that is going to be later on. I will share that project. For the overall project, for the mass of the box beam versus UHPC comes out to be around 45% less mass because you use less material and it's a slender material section and goes a longer span. And then the embodied energy, there's some savings of about 15%. Which translate to all the carbon dioxide emission, about 7% reduction, and then the global warming potential, which is your gas greenhouse gas emission, is like 5% reduction. So this is environmentally there's some impact going from a normal concrete box girder to UHPC beams. So UHPC Decked I Beam development, the cross section was actually jointly developed by eConstruct and ourselves, and it's basically to promote accelerated bridge construction using the least number of precast pieces. Minimizing cast in place usage. Okay, so UHPC has a superior durability properties for freeze-thaw and saltwater contamination. It's suitable for the Canadian climate. I'm sure also for the U.S. Superior tensile strength and least concrete volume. So here is the 3-dimensional view of one of the beam. So in this case here, we are showing the post-tension segmental section, but the product can be pre-tension as well. And there are some dimensions here. Basically, the top flange, in order to save some material, we make it like a waffle. You can see the section, there are some ribs. The ribs is in one direction only. So it's like a T-beam, if you want to simplify it. Now, what are the challenges here? Because it is, you had to cast it all together in one go. There's the formals are more complicated. and then you need to deal with the crown, the bridge crown, or even super elevations, right? So the flange to flange connection requires the flange edges to be totally aligned, possible to use a clamping mechanism. And then also because the ribs are further apart, we have to use some high strength steel like the Chromax in our design. And then in between the UHPC beams, they are connected by a UHPC cast-in-place closure strip. So this is one of the forming concept. Quite complicated. So we cast one girder as part of the PCI project. It's a 15 meters long girder and a 1 meter section, and in our yard, and we have that tested in North Carolina State University. So there are some pictures here of the girder form of the prestressed girders. Okay. UHPC batching, we don't have a mixer that can cast the beams all together, the 15 meters. So we use 3 smaller mixers. One of them is a Skako, which is 0.5 cubic meter or around half a cubic yard, and 2 pan mixers. And then it is a very intensive casting for almost a day, almost an 8-hour day. And it just continuously, that 3 mixers, the longest time between casting is about 15 minutes, so because we need to wait for the 3 mixers to finish dumping the concrete into the bucket and then cast and then discharge them. So ice were used, and also workability air mixtures. Okay. So the batching sequence. So basically, we did all the premix, all the dry powder first, and then add fibers. You can see in the pictures there, like we add some ice. Girder placement. We build a special chute so that we just cast the lower bell, the lower flange, the bottom flange, and the web at the same time, from one end to the other end, and then come back and cast the top flange. So, like it says here, after the concrete filled the web on the bottom flange, pouring of the deck started. But because when we cast the bottom flange and the web from one end to the other end, and then when we come back to cast the top flange, the first batch of concrete that was cast was about an hour all. So then we need to use some kind of a vibrator to agitate to ensure that we have a good bond. But we did add some dowels to ensure that we're not losing that interface shear. So the deck finish, we use some rubber matting to make that rough looking surface. Okay, so then we have the girder cure. You can see that it was cast like in February, and it was still snow. There's still snow on the ground. So the steam curing is for 90 degrees Celsius for 2 days. So here we have that curing and post-curing temperature profile. You can see the peak there, which is the 90 degrees for the 2 days. Quality control. This is we need the cylinders for all kinds of people. We need to send to North Carolina State University so that they can test it together with the beam. We need to send to WJE, which is the materials consultant for the PCI project. We need to do some ourselves. So that's a lot. And then Corina's folks help us with testing in Ontario. So testing at North Carolina State University. So the girder was shipped on February the 21, 2020. If you remember, that is just at the beginning of almost at the beginning of the COVID. And so by the time it get to North Carolina State University, actually the university was in the lockdown. So it was a big problem to get in to test the girder. Okay, so anyway, they did manage to test them, and flexural testing, basically testing the girder right at the midpoint. But we did not. We just ensure that it meet the load requirement and not try to damage the girder. That's why, because we only have one girder. So the flexural testing, it was stopped at some point to make sure that it meets the design load. Now for shear testing, what we have here is that because we only have one girders, and half of the girders we don't have any stirrups. The other half we have stirrups. So that's by design. We make it that way so that we want to show that UHPC beam actually doesn't need stirrup. Okay, so that was the aim. So then the shear testing. This is a site with the no stirrup. You can see that the service load is way below there, and the factor load, and basically the failure load is about 2.5 times the design load. So you can see this is the shear failure, and then there's the steel fiber bridging the cracks, and then there's the video here. How do I do this? How do I do the video? Okay. Then we test the site with the stirrups. We didn't get a shear failure. It fell in flexure because of the stirrup actually. So you can see from here, the cracks actually kind of line up with, he marked where the stirrups are in red, and you can see the stirrups on the right hand side there. There's a video here. So with the stirrup, you can see the failure is different. It's a shear failure. It's not a shear failure. So we do have semi-integral diaphragms, and we test that. And then, I'm not going to go too much into this University of Nebraska. They were testing quite a bit of that too. And there's a potential new project, I say, in Ontario, which we are pursuing with WSP folks, is to replace box beams side by side with the UHPC girders. Here's some integral abutment details, semi-integral diaphragm option that we can do too. Anyway, conclusions: use of UHPC precast UHPC is environmentally responsible and cost-effective. Structural products can be produced in current precasting facility with minor equipment modification. Quality control must be a top priority. Excellent structural performance in full-scale testing by 2 universities. Testing demonstrated conservative design. We try to improve on that, optimize it. Eliminate discrete mild steel shear reinforcement using a narrow 4-inch web. Okay? Thank you.
Thank you very much, and thanks for being on time. We can have a couple of questions if anybody has questions.
Just a quick question. I think you showed some pictures of fibers. What types of fibers were in addition to steel fibers?
We just use steel fibers.
Okay.
Yeah.
So the question is, what's the dose and what kind of fibers?
Yes, we used 2% by volume, and the fibers that we had is 20 millimeter long, which is I guess 3/4 inch, and then 0.2 millimeter diameter. Straight, yes.
There's one more question. What was the contact strength though? At the time of testing.
At the time of testing, I know that we steam cure it. It was at when we ship it, it was what 160 MPa EMAT. Yeah, yeah.
The question is, did you conduct direct tension tests?
We at the time we don't. Well, I mean T397 method was not really available yet, right? So we didn't do it. But at this time, we are doing some direct tension testing. Yes.
One last question, and you'll be. Or do they break?
It's they just pull out. There's no breaking. Yeah.
Thank you very much.